Alrighty, we're getting ready to tackle linear functions pretty quick here in the next lesson, lesson 55, especially piecewise linear. But it just seems like a good idea to sort of review some of our old straight line stuff like slope formula and slope-intercept form and stuff like that. So let's start with the slope of a line. Here's a definition. We can indicate how steep a line's slant is using a ratio, the ratio of rise to run. This ratio is abbreviated with an M, so M stands for slope. Sometimes I try to say mope, but it's not usually that funny. But M comes from the French word monter, which is to climb or to go up, and so we're measuring the steepness, and we're calling it M. So again, it involves making a ratio, which means a fraction, which means something on the top, something on the bottom. Rise over run. Okay, so let me draw some kind of a line in here. I got this grid here. I'll just draw a line anywhere. How about if I do something like this? This is a line, right? Sure, that's a line. We'll talk about this line right here. So the idea is you should be able to take any 2 points on the line. How about that one? And then let's find another point on the line. How about that one? There's a point. There's a point. Take any 2 points on the line. Any 2 points. Emphasizing that point. And then you sort of get out your ruler, or in this case we don't need a ruler because it's lining up so nice on the grid points. And you measure two things. You measure how high up do we go and how high over do we go. This part's called the rise, the how much up, and this part's called the run, the how much over. So this one here looks like it has a rise of 1, 2, 3 grid points. It's kind of nice that it's coming out on the grid points. Otherwise, you'd have to use a ruler, which you can do. But anyway, it's a rise of 3. And then you measure the run, and you go, okay, so from here I'm going over. 1, 2, 3, 4, 5, 6. 6 squares or 6 whatever you want to call them. 6 whatever you want to call them. 6. So if you have a rise of 3, if we have a rise of 3 and a run, and I want to maybe put this in a different color here. The run is always left to right. When you're talking about a run, you always go left to right. So I'm going left to right when I talk about my run here. So anyway, the run is always left to right. So I went up 3. I definitely went up. I went up 3, and I went down, and I went over 6. And so the rise over the run is a 3 up and a 6 over. And yeah, you should reduce that. Reduce it to 1/2. So the up and over, the rise to the run is a 1/2. Notice it's the ratio that's important. New color. It's the ratio that matters here. For one thing, you know that I reduced it. 3 to 6 reduces to 1/2. But you can see that over here too. Up 1 over 2. Up 1 over 2. You know, if you wanted to, you could have gone like this. Up 4 and over, I bet you it would have been 8. Up 4 and over 8. Well, a 4 up and an 8 over, that reduces to 1/2 either. You could go up 40 and over 80. You could go up 4,000 over 8,000 and so on, right? So again, it's the ratio that matters. I want an eraser. I want an eraser. Give me an eraser. Okay, let's erase some of this stuff because I don't want to get this too clogged up. Maybe I'll even erase those things. That's the idea of slope. There's another interpretation of slope. And this is actually a good one, and we're going to use it too. So another interpretation of slope. Let's kind of squeeze this in here. Rise over run. Hopefully you've heard that somewhere before. It seems to be a pretty popular phrase. Another interpretation of slope, which is quite handy really. It goes like this. It's how much y changes, how much your y-coordinate changes when x increases by 1. And to illustrate this, what I'll do is I'll zoom in on this part. Zoom in. So I'm trying to circle a few dots there. So I'm circling those 6 dots, and the line is coming across like that, right? There's our line. And if you look right about here, and I guess I need another color again. If you look, this would be increasing x by 1, right? Increasing x by 1, how much does y change? And you'll see it comes up by half. Comes up by half. And hence the interpretation. How much does y change when x changes by 1? It went up by a half. Now, the reason this works is because if you make a ratio of rise over run here, you're putting a 1/2 over 1, and guess what? That's a half, right? So it works. It obviously works, but this is a very, very nice interpretation that we're going to use in lesson 55, like I say. So, for example, I don't know, widgets are $5.65 each. Guess what the slope of the line is going to be if you make cost versus how many you bought? It's going to be $5.65, because if you buy one more, the cost goes up $5.65. So that cost each is your slope. It's kind of handy. And if you're not accepting that right now, that's fine. We can come back to that later. So let's just get back to this working in the abstract slope type stuff. Okay, rise over run will do us very good. Now this slope gauge, what I wanted to do here, sometimes to get used to working with slopes, it's good to kind of, doodle a little bit. So I'm just going to start here. I'm just picking that point arbitrarily. I want to draw a line that has a slope of 1. What would I do? From this point, I would have to go up 1 and over 1, which would get me to there. Up 1 over 1 gets me to there. Up 1 over 1 gets me to there, gets me to there, gets me to there. So when you go this way, this is the slope of, well, it's a 1-to-1, up 1 over 1, which of course you can just write 1. So that's what a slope of 1 looks like. Now if I went down 1 over 1, down 1 over 1 instead, I'd be going this way. Now that can't be a slope of 1 because we're already using a slope of 1 for that line. That line has a slope of 1. So what's the slope of this one? Well, since it's going down 1, hey, what'd you do? Since it's going down 1 over 1, we would say the slope is, well, basically the rise is negative, right? Down 1 over 1. Always left to right when you're doing the run. Always left to right. But the rise, sometimes it goes up, sometimes it goes down. What are you going to do? But you could call this -1. But that's a slope of -1. So positive slopes, positive m goes up, negative slopes go down. Okay, just something to keep in mind. Positive slopes go up, negative slopes go down. I'm going to do, starting at the same point, I don't have to, but I will. I'm going to start at the same point. I'm going to do a slope of like, how about 1/3? Up 1 and over 3 is what I'm after here. So up 1 over 3 gets me to that point. If I do it again, it gets me to that point. If I do it again, it gets me to that point. Here's what a slope of 1/3 looks like. Okay, so this is kind of fun. Here's a slope of 1, here's a slope of 1/3. We're having a ball. -1/3, yeah, let's do that too. So I would want to go down 1 and over 3, get me to there. So it gets me to did I go there? 1, 3, yeah. Go down 1 and over 3 gets me to there. Go down 1 over 3 gets me to there. So here's what a slope of -1/3 looks like. Now, from just drawing these lines, from just thinking about these 4 lines, you see a 1, you see a 1/3. Okay, come from here. You see a -1, you see a -1/3. What do you suppose is in the middle? A line that goes sideways. Well, the slope has to be, somewhere between the 1/3 and the -1/3. That helps me to remember that if you have a 0 slope, it's a horizontal line. So a 0 slope goes straight across. Now, another way of remembering that, of course, is the rise is 0. You never rise. Between any 2 points on this line, there is no rise. There is no rise. The rise is 0, so the slope is 0. So that line has a slope of 0. So that's a 0 slope, that's a fraction slope, that's a 1. Let's do a 3. Up 3 over 1 gets me to there. So it gets me to there. Up 3 over 1 would get me to about there someplace. So here's a slope of 3, and of course you can drop 3 and go over 1. Drop 3, go over 1, gets you to there. That would be a negative slope, of course. So this is a slope of negative 3. So, you know, somewhere in between here is a slope of 2. Somewhere in between here is a slope of, you know, fractions that are bigger than a third and less than 1, half, 2/3, whatever, and so on. So it gives you an idea of, you know, if somebody gives you a slope number, you can sort of get a quick idea of where it is. And one last one to draw. What if the line is actually vertical? Well, then you rise for, you pick any 2 points you want, right? So your rise is going to be whatever, but notice when you divide by the run, you're dividing by 0. Whoops, not supposed to do that. And so that's called undefined. So that would be an undefined slope. Dividing by 0, bad idea. So this, a vertical line has an undefined slope. We're not gonna play with vertical lines very much. They're not good. You can't really write their equations very well or anything. They're nasty. But anyway, we got this idea of slope. Rise over run, rise over run. It's a ratio, rise over run. You can reduce the ratio, rise over run. Okay. Here's the slope formula, which, by the way, rise over run. This is how we usually say it, I guess. Maybe I'll just kind of write that down. I'll say usually how we say it. I like to say it this way, change in y over change in x. You'll hear me say it that way a lot. Here's the main formula right here. This is the most often used formula. This formula is exactly this, is equivalent, I'll say. It's exactly equivalent. You can use this formula if you want. What's the difference? This formula says y2 minus y1, x2 minus x1. This one says y1 minus y2, x1 minus x2. What's important is that they're both going in the same sense. 2 minus 1, 2 minus 1, or 1 minus 2, 1 minus 2. You would not want to go y2 minus y1 over x1 minus x2. That's not going to work, okay? You can't just subtract any willy-nilly way you feel like. Okay. It's equivalent. I invite you to, you know, play around with both formulas and you can convince yourself pretty quickly that, yeah, they both work. Well, I can explain really. It's because when we say take any 2 points on the line, it doesn't really matter which one. If you want to call this point 1 and this point 2, then the rise goes from here to here, you know, whatever. But if you wanted to call this point 1 and this point 2, it doesn't matter. It doesn't matter. And so that doesn't, as long as you go in the same sense. But anyway, let's practice using this. So here's a nice one, and I think I'll sketch to do this one. We have these 2 points, and they're nice points. And when they have nice points, often you can sort of bypass the formulas and just kind of get it from the graph. Negative 4, 6. 1, 2, 3, 4 to the left. 1, 2, 3, 4, 5, 6 up. That puts me there. Negative 4, 6. That's a 6. Negative 4, 6. Okay. 8, negative 2. Come to the right by 8. Down by 2. That's over here someplace. 8, negative 2. Well, they're kind of far apart. But that's okay. We can still, because they're nice landing up on the grid lines so nicely, we can just kind of, you know, do our little triangle construction here. Or I guess this, well, it would be a triangle if I did this. Do our little triangle construction. Here's the rise, and here's the run. The run always goes left to right. And so the run is, and you can just count the squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have a run of 12. Now the rise, we're going down. That's kind of like a negative rise. But the rise, you count squares again. 1, 2, 3, 4, 5, 6, 7, 8. We're going down by 8. And so the slope of this line, if you do rise over run, And you keep in mind that the rise is actually negative. It's going down. Remember from our slope gauge, right? Negative slopes go down. So the rise is down 8, negative 8. The run is 12. And always reduce, right? Put the negative out front. It's neater. But cancel 4s here. The slope is negative 2/3. Now, if you want, you can use the formula. I'll use the formula just for fun, just so you see it used once. What you would want to do is you'd want to, maybe I'll do purple. Take one of these points and call them point 1. Take the other one and call it point 2, and it doesn't matter which is which, as long as you stay consistent. But I'm going to call that point 1, and I'm going to call that point 2, which means that's my x1, that's my y1. That's my x2, that's my y2. So if I start using that formula, maybe I'll shove it over here somewhere. y2 minus y1 over x2 minus x1. What does that look like? The y2 is a negative 2. Formula says minus. The y1 is a 6. The x2 is an 8. The formula says minus. The x1 is a negative 4. So on the top, minus 2 minus 6 more is minus 8. On the bottom, 8 minus a negative means add 4. That's a 12. And of course, we're getting the same thing. Negative 2/3, just like before. So the formula is cool too. So if you got some funky points like these, I don't know if I'd want to draw a graph of 2 1/4, 1 7/8, and that might be kind of hard to get it. So it's still not a bad idea to sort of draw the graph just to get an idea what you expect. What are we expecting here? 2 1/4, 1 7/8, somewhere over there. Negative 4 1/2, 3, somewhere over here. We're expecting a negative slope of some sort. Probably a fraction, right? Because remember, for it to be a slope of negative 1, it would be going down at 45 degrees. This is less than 45 degrees. So we're expecting some negative fraction. But let's actually get it now. Let's use the formula. So I'm going to call that my x1 and my y1. I'm going to call that my x2 and my y2. So the slope, the rise over the run, is the change in y over the change in x, isn't it? y2 minus y1 over x2 minus x1. And what do we got here? y2 is a 3. Minus. y1 is a 1 7/8. Oh boy. x2 is a negative 4 1/2. How nice. Minus. And x1 is a 2 1/4. Okay. So now we got to do this stuff. Please, calculator should stay in the drawer for most of this course. You're learning to play with numbers. That's a good idea. Learning to play with numbers. That's how you develop your number sense, is you play with the numbers. Anyway, first thing I'm going to notice is that I got fractiony things going on here. So I'm going to take that 3, think of it as a 3 over 1, just so it looks like a fraction. Now this 1 7/8, remember how we do that? You go the 8 times the 1, and then you add the 7. Let's see, what's that, 15? So that's a 15/8 on the bottom. I got a negative. Do the same thing with the 4 1/2. 2 times 4 is 8, plus 1 is 9. So that's a 9/2. Negative in front, minus. And this will be a 4 times 2 is 8 plus 1. That's actually a 9/4. Okay. Now's the part where you need your common denominators, right? You cannot add or subtract a fraction unless the denominators are common. On the top, it looks like we're going to need 8s. So I'm going to multiply this fraction by 8/8. Remember, 8/8 is the same as 1. So if you multiply it by 1, all you're changing is the way it looks, not its value. On the bottom, our common denominator is going to be 4, so I'll have to multiply this fraction by 2/2. 2 over 2. So what is this giving me now? On the top, I'll have, let's see, you just multiply straight across. 24/8 minus 15/8. On the bottom, I'll multiply by 2 straight across. Negative 18/4 minus 9/4. Okay, let's bring it down to here. So on the top, that's a 15. So 24 minus 15 makes a 9/8 on the top. On the bottom, a negative 18 minus a 9 makes a negative 27/4 on the bottom. Now, first of all, to notice that when you take what's a positive and you divide it by a negative, your answer is going to be negative. Just put the negative out front. We know it's going to be a negative slope. And by the way, we knew that going in, didn't we? We knew it's going to be a negative slope. Okay, cool. Now, how do you unstack one of these big old fractions? What you have to do is you have to think of the fraction. Well, you don't think of it this way. It is this way. You take the number that's on the top and you divide it by the number that's on the bottom. That's how fractions work, right? Did you ever convert 1/2 into a decimal? How do you do that? You go 2 into 1 and you get 0.5. Okay, that's what fractions are. It's the top being divided by the bottom. So anyway, that's what they are. So if you have big ugly fractions, you can use that idea to make them look less big ugly. So take what's on top, 9/8, and divide it by what's on the bottom, 27/4. And I've already taken care of the negative. It's out here. I know the answer is negative. Then comes the part where you say, oh, but that means when you divide by a fraction, what you're really doing is multiplying by the reciprocal. Okay, cool. We're getting somewhere. Now's the part you can save yourself a lot of energy if you sort of cross-cancel before you multiply. So 4 goes into 8 twice, right? 9 goes into 27 3 times. Cross-canceling first, that's the way to live your life. Now, that only works when you're multiplying fractions. Only multiplying, only multiplying, only multiplying. But if you're multiplying your fractions, go ahead and do the cross-cancel first. So I've got a negative. 1 times 1 is 1. 2 times 3 is 6. There's my slope. It's a negative 1/6. Woohoo! Hope you enjoyed that. Now, keep in mind, if you ever need to remember how to do this fraction action, you can say, oh yeah, there was a nice example in that video lecture. I should go back and look at that if you're ever forgetting how to make these moves, these various moves. Okay, so 2 pages down, 2 to go. The next 2 are faster, I think. But now that you know how to play around with slope and how to interpret slope and stuff like that, now things get cool because we can start playing with actual lines. So what I'm going to do is I'm going to graph a line here, but first I'm going to do it the old way. What does old way mean to us? I mean, just make an XY table. Let's just make an XY table. This is the old way. It's not a bad way. But let's see. Now I'm looking at this, and usually you want to center your shotgun, so to speak, somewhere in the middle, like at x equals 0. And just right away, if I plug in x equals 0, I've got 2/3 times 0 is 0 minus 1. Okay, there's our first point. That's a nice point. Now let's be a little strategic about plugging numbers in. We're going to be multiplying things by 2/3. Wouldn't it be nice to have a multiple of 3 so that the 3 would cancel? Let's use a 3. Suppose I should write the whole thing. This is 2/3 x minus 1, right? Right. So if I use x equals 3, the 3's will cancel. I'm looking at 2 minus 1 is just 1. Wasn't that beautiful? And, you know, while I'm at it, let's make that into a -3. So now I've got the -3 cancels to a -1. So now I've got a -2 times a -1. Pardon me, talking too fast here. So I have a 2. Sheesh. So I have a 2 times a -1 is a -2, and then you subtract 1, you've got a -3. So when I use a -3, I actually get a -3. How do you like that? That's weird. Okay, now 3 was working really well. Let's get this out of the way. How about we use another multiple of 3? We'll use a 6. We'll use x equals 6. So coming down here, if I use x equals 6, what happens? The 3 cancels into the 6 twice. I got 2 times 2 is 4. 4 minus 1 is 3. There's a point. And now let's just do a -1, a -6 as well. So if I do a -6 instead, what will happen is when I cancel, that'll be a -2. So now I've got 2 times -2 is a -4 minus 1 is a -5. Okay, and now I got some beautiful points to play with here. So when x is -6, go to left 6, down by 5, -5, right about there. When x is -3, go left 3, I go down 3, for y is -3. When x is 0, y is -1. When x is 3, y is 1. When x is 6, y is 3. And you'll notice those all line up on a beautiful straight line. And we join the line to show that all of these points are also solutions to the equation, right? You could plug in x equals -2 point whatever, and you'd get y equals whatever it is here. So anyway, all those points are solutions to this equation. We've got a nice line. Now, I got a big deal here. This is a big deal. what you do is you take a look at this thing. And I want you to notice a couple things. First of all, notice that when you go, let's say from this point to this point, notice you go up to and over 3, right? So I'm going to call this cool fact number 1. The line here, it has a slope of positive 2/3, and what's cool is, if I get this stuff out of the way because it's a mess, what's cool is the 2/3 is right there. That thing was telling you straight away, oh, by the way, your line's going to have a slope of 2/3. It has a slope of 2/3, and that's x's coefficient. I'll just abbreviate it COEFF, coefficient. That's a nice, cool fact. So in other words, just looking at your equation, you say, oh, see the x there? It says times 2/3. That's called the coefficient. That's my slope. Cool fact number 2. You can see that it crosses the y-axis at -1. So this thing has a y-intercept at -1. And where do you see a -1 in this equation? Right there. And that's the constant term in the equation. We call that a constant term because it doesn't multiply an x. It's just a number. Exclamation point. Cool fact number 2. So that's the B. So in other words, the big deal here, to finish writing it out, the big deal is this formula fits a really nice form called slope-intercept form. The coefficient of x tells you the steepness of the line, the slope. The constant term over here tells you the y-intercept. Again, this is called the slope-intercept form of a line. So whenever you see an equation that has this kind of a format to it, you say, oh, that's a straight line. And not only is that a straight line, I even know what the slope is. I even know what the y-intercept is. So you come down to this one now, the second example here, and you say, huh, that's slope-intercept form. I can tell by looking at it. See the coefficient there? The slope of this thing is -3/2. I can tell by looking at the constant term. The B is 2. And if I know that, I don't need no stinking XY table. I don't need it. I don't need it. I'll start here with the B. The y-intercept is 2. So I come up to the y-axis where y is equal to 2, and I go, boom. That's my y-intercept. So I did that first. I'll put a 1 there. And then, maybe I won't put the 1 quite there. I'll draw the 1 later. And then I say, okay, part 2, the slope is -3/2. Now, the line is going through this point, right? So I've seen people start at the origin and go down 3/2. You don't want to start at the origin and go down 3/2 because the line's going through that point. So you start at this point and you go down 3/2, right? Down because it's a negative slope. And that's your next point. And then you keep doing that, down 3/2. There's your next point. And you try to be neat about it. You can go backwards too. Instead of down 3/2, do both of those things backwards. Up 3 back 2. There's another point. And so anyway, there's our line. So I did the y-intercept first, and then I did the slope second to get these more points. Now, isn't that nifty, right? You save yourself all the trouble of an XY equation. Not only that, not only does it help you to draw the graph, but you can picture the graph in your mind immediately. You just look at the equation, you say, I know what that looks like. Yeah, start at 2, go down -3/2. Yeah. I know what that looks like. So you can almost like just talk about the line without even graphing it to some extent. And I'll just put a little aside here. P.S. If you ever have any doubt about whether you drew it right, about whether you drew it correctly, and it's important to be, it's important, well, especially in this course with my no partial credit policy, it's important to be sure about your work, right? It's important to check it. But so if you ever have any doubt, you can always just plug in some random value and make sure it's landing on the line that you drew. Okay, make up a number between, this is -6, this is +6. Make up a number between -6 and +6. How about, I don't know, how about -2? I just made that up. So you go to your equation, y equals -3/2. X is, we're going to use a -2, put it over 1 so it looks like a fraction. And let's just see what we get here. So the negative times the negative cancels. This 2 cancels this 2. So that's basically a 3 plus a 2, which is a 5. We're expecting 5. And then you check. When I just plugged in x equals -2, 1, 2, 3, 4. It worked. So that doesn't count as a proof, but it certainly gives you a lot more confidence because you just arbitrarily chose a value of x and it worked. So it's probably pretty good. Okay, so now we know what this slope-intercept form of a line is. Now, the last page, this is what we really got to do, especially to help us get ready for lesson 55. We need to be able to, given some information, find the equation of the line. Make the equation. So I got 3 examples here. So, for example, let's say we know 2 points. The line goes through these 2 points. Let's just draw them. Sometimes it really is nice to just draw things. Sometimes you can save yourself a lot of trouble because if you always jump to the formulas, then guess what? You're always stuck cranking out formulas. But if you have nice numbers, say, you know what? I bet you I might be able to just get that by graphing it. Get this information right off the graph. So I plotted the 2 points. Can you tell what the slope is? You can tell what the slope is. It's positive for one thing because we're going up, right? But notice we're going up right along at a 45-degree angle. That's a slope of 1 if you remember from your slope gauge. Or another way to think about it is I'm going up 3 over 3. That's a 3 to 3 ratio. Up 3 over 3 reduces to 1 to 1. It's a 1. So the slope is 1. That's awesome city. And if the slope is 1, then you just kind of go back 1, down 1, back 1, down. You can figure out where the y-intercept is because it's crossing so nicely on all of these crosshairs or whatever you call them, on all the grid intersections. I don't know what you call this. Anyway, you can tell right there the b is -2. The m is +1. The b is -2. What's the equation of a line now? It's mx plus b. Well, I know that the m is a +1. I know that the b is a -2. And so that tells me that the equation of the line is this. Which, if you want to write it a little more simply, you don't have to say +1 times x. You could just say x. It means the same thing. So look at that. Wasn't that nice? No formula, no muss, no fuss. So, and besides, it's nice too to just realize the geometric, is that what you call it, a geometric connection? But just to realize that there's pictures of these things that goes with all the number crunching and formulas that we're playing with. These things apply to real pictures and stuff. So the first one didn't take too long. Second one, a line, let's change colors here. A line passes through these 2 points. What's its equation? Well, maybe I'll try using that same graphing grid up there. -2, 5 would be back 2, up 5. That'd be right about here. 4, -3. 1, 2, 3, 4, -3. Well, I'm kind of on top of myself, but okay. Well, I'm having a hard time here. I can at least get the slope off of this because I can count, draw my little triangle type construction here. I come straight down from this point, I come straight left from this point, and I can count squares. 1, 2, 3, 4, 5, 6, 7, 8. So the rise is actually a negative rise because it sinks. And the run is 1, 2, 3, 4, 5, 6. And so I can tell just by looking at a graph that the slope, which is rise over run, is a -8 over a 6, which reduces to a -4/3. Just cancel 2's. that's the slope. It's not the equation of the line, but it's the slope. Now, if I wanted the y-intercept, I'd have to look at where is it crossing the y-axis, and I'm not sure I want to try to... I could squint, I suppose, and try to read that, but I got a better way. That's supposed to be an M. I got a better way. Okay, so to get the... Yeah, let's stay in green. To get B, we have to think like this. Think like this. The equation of the line is y equals mx plus b, but we know what the m is. So there's the part we don't know. We don't know what the b is. Okay, so you could start writing the answer, but you don't know what the b is. Okay, so we know that, well, this point is on the line. What does that mean? If we plug in fact, let me write this a little bit more carefully. Since the point 4, -3, and it doesn't matter, I could use this point instead if I wanted to. Both points are on the line, right? So it doesn't matter which point I'm looking at, but I just grabbed that one at random. So since that point is on the line, it must happen. It must happen, that's a must. It must happen that plugging in x equals 4 will give us y equals -3. Because if you think about making the xy table for this graph, right? When you plug in x equals 4, it's supposed to tell you that y is -3. So let's make it happen then. So -4/3, so I'll put a big so. -4/3 times the x is 4, and when I plug in whole numbers, I usually put them over 1, plus b is supposed to come out to -3. This is the big breakthrough moment. So we kind of had this much information. We knew the slope. We got the slope easy. We knew the slope. So we said, okay, mx plus b. I know the m is -4/3, so okay, I can put that in. How do I get the b? Well, I have this other piece of information. I have this point here. I know that when I plug in x equals 4, the equation has to tell me that y equals -3. So I'm plugging in x equals 4 into my formula, plus b that I don't know what it is yet, but I know that it's got to give me a -3. Woohoo! So let's finish this up then. So this would be, if I multiply these two, I get a -16/3 plus b is equal to -3. So you have to add, let's make that look like a fraction. You have to add the 16/3 on both sides. So a -3/1, I'd have to multiply by 3 top and bottom, right? Plus 16/3, which is 7/3. That's my b. That's my b. That goes here. And so my final answer will be, and I'm going to put my answer up here, I guess, y equals -4/3 x plus my b came out to 7/3. That is my final answer. This is actually a very common maneuver. It's like, hey, I knew the m, but I didn't know the b. I didn't know the b, but I did know the coordinates of a point. The equation was supposed to work at that point. And so you plug the point in, and then you can actually solve for the b because you know everything else. You know what the x is, you know what the y is, you know what the m is. What you don't know is the b, so you solve for it. So this is a very common trick, and we're going to use it again like right now. Let's use it right now. Now first, let me see if I can kind of get this stuff out of the way. You are in the way. So I'm going to shrink it, maybe move it over there. Okay, cool. So let's look at this one. What color do I feel like working with? None of these colors look all that good. I'll take the brown. I'll take the brown because it's very different. Okay, we end with our big one. Now this one's going to be the most computationally intensive, if you will, because look, we got fractions and stuff. Am I going to draw that on a grid and hope to read the answer off the grid? No, I don't think I'm even going to try. I'm just going to say this is 0.1, which means that's my x1 and y1. This is 0.2, so that's my x2 and y2. I want to get the equation of the line, and that means I have to solve for two things. I have to find the m, and I have to find the b. Now the m, luckily, there's a nice formula that you can get m straight away. Well, not that straight. You have to calculate it. But anyway, the formula says y2 minus y1 over x2 minus x1. All right, here we go. So the y2 is a 2/3 minus the y1 is a 4. I'm going to write it as 4 over 1. On the bottom, the x2 is a -1, which I'll write as -1 over 1. And then minus the x1, which is 3 1/4. What's this stuff? Well, here I need to use a common denominator of 3. So I'll have a 2/3 minus multiplying the 4 and the 1 by 3 gets me a 12 over 3. That's up there. On the bottom, if I do the fraction on the right first, okay. If I do the fraction on the right first, 4 times 3 is 12 plus 1 is 13. That's a 13/4. And then, so I know that the 1 over 1 I should multiply by 4 over 4 and make that a -4 over 4. Okay. I needed a common denominator of 4. So up here I can do the subtraction now. 2 minus 12 is a -10/3. And on the bottom, -4 minus 13 is a -17/4. Notice that the two negatives are going to cancel. We're going to get a positive something. Take the fraction that's on top and divide it by the fraction that's on the bottom. Let's come over here now. So I'm going to take the 10/3 that's on the top and I'm going to multiply by the reciprocal of what's on the bottom. Boy, it'd be nice if something canceled, but nothing's canceling, cross-canceling. 10 times 4 is 40. It is what it is. 3 times 17. 3 times 10 is 30. 3 times 7 is 21. 30 and 21. It's a 51. So our slope is that nice number, 40 over 51. Okay, cool. So y equals mx plus b means that we know that y equals 40 51s x plus b. We need the b, which means now, let's change this to, can I highlight in brown? What will that look like? It worked. Okay. So to get the b, I should look at these 2 points and pick one. And I think I like the idea of plugging in x equals -1 instead of 3 1/4. So let's not pick that one. Let's pick this one. So I'm going to use that point. So I'm going to say I have a point that when x is -1, y should come out to 2/3, colon here. And so what does that tell me? It tells me that when I take the 40 over 51 times x, when I plug in x equals -1, which, I mean, I suppose I could write it this way if I wanted to, plus b, right? I should get y equals to 2/3. We're almost done. We almost have our b. Good thing I can scroll down, huh? So when I multiply 40 times -1 over here, I'm getting a -40 over 51 plus b equals 2/3. And so what's b then? b is 2/3, and you add this to both sides, 40 over 51, add to both sides. Now I need a common denominator. The good news is 3 does go into 51 evenly. It goes exactly 17 times. So you take that first term times by 17 over 17, you get a 34 over 51, adding the 40 over 51, and you get a 74 over 51, and that's our b. So change color for the magic answer here. So y equals mx plus b. We know what the m is. The m is 40 over 51. And we know what the b is. The b is 74 over 51. Let me spot check. Yes, that's what I got before. I'm so happy when that happens. There's our answer. Yeah, it's got some funky fractions in it, but you know what? Fractions happen. Fractions happen, especially when you're trying to be precise. When you're trying to be precise, you don't like to carry along 18,000 decimals that all got rounded off. You know, if the answer is precisely 40 over 51, then that's what you want to use, 40 over 51. And you know, fractions happen. You might as well get used to them. They're good. They're happy. The more you get to use them, the more you like them. Something like that. So anyway, there's our nice review / maybe pushed it just a little bit, pushed the envelope just a little bit on our straight lines. We'll be ready for lesson 55 now.